Almost everyone believes that a computer would overheat immediately in space. In reality, the exact opposite is true. Cooling is easier in the vacuum of space than on Earth. And it's precisely on this one fact, which goes against all intuition, that SpaceX is currently making a bet that could hardly be bigger. Because the artificial intelligence that we all use every day has hit a wall here on Earth. A wall made of electricity, water, land, and resistance. And SpaceX's answer to this is so radical that even the head of rival OpenAI has publicly called it ridiculous. They want to take the data centers off Earth and shoot them into orbit. At the center of this plan is a single satellite with the simple name AI-1 or KI-1. Or KI-1. And perhaps the craziest thing about it is that it's built even simpler than an ordinary Starlink satellite. My name is Serwan and this is Mars Chronican. Let's start with the problem, because without the problem, you can't understand the whole bet. Artificial intelligence consumes computing power, and computing power consumes energy. According to common forecasts, the electricity consumption of data centers worldwide will double by 2030. And by the year 2050, it could account for about 1/10 of all the electricity consumed on Earth. In North America alone, an additional demand of 50 to 100 gigawatts is expected over the next 3 years just for new data centers. For context, an average nuclear power plant produces about 1 gigawatt. So we're talking about the energy demand equivalent to 50 to 100 new nuclear power plants. And that's just on one continent. On top of that, you need land and gigantic amounts of cooling water, and there's less and less room on the ground to deal with the waste heat. That's exactly why new data centers are facing resistance everywhere. And in major US markets, a new building today has to wait 5 to 7 years just to get connected to the power grid. And this is where the really big, almost absurd idea comes into play. Elon Musk puts all of this into the so-called Kardashev scale, named after a Soviet astrophysicist. This scale measures the progress of a civilization not by wars or economic output, but by a single number. Namely, by how much energy it can control. Type 1 controls all the energy of its planet. Type 2 controls the energy of its star. Type 3 controls the energy of its entire galaxy. And now comes the sobering part. Humanity currently uses far less than 1/trillionth of the energy our sun emits. We are practically unmeasurable on this scale. The sun is so incredibly massive that it makes up about 99.86% of the total mass of our solar system. In comparison, the Earth is hardly more than a speck of dust. Musk's argument is simple. If you want to take even a tiny step up on this scale, you have to go into space. Because on Earth, the usable area for solar energy is limited. 70% of the planet is water. A good part of the rest is desert or polar region. In the right orbit, sunlight is available almost continuously, without night, clouds, or seasons. And that's the crucial technical point. Cooling is actually easier up there, not harder. We need to take a closer look at that because it's the core of the whole story. Musk breaks the project down into 3 bottlenecks that need to be solved, and I'll structure the entire video for you around these 3 points. First, you need the ability to launch enormous mass into space. Second, you need a lot of solar power and proper heat-dissipating radiators. Zur Wärmeabfuhr. Third, you need an almost unimaginable amount of powerful chips. Let's go through them one by one. The first bottleneck is mass, and this is where Starship comes into play, which we've dedicated an entire video to, and I'll link it below. The short version: Starship is the first rocket designed for complete and rapid reuse, and it's by far the most powerful flying machine in history. The current version 3 delivers more than twice the thrust of the Saturn V moon rocket version 4 is expected to achieve almost 3 times as much. What's crucial is the shift in scale this creates. Even today, SpaceX transports about 85 to 90% of all the mass that humanity sends into orbit with Falcon 9 and Falcon Heavy. With Starship, SpaceX wants to jump from about 2,500 tons per year today to millions of tons per year. And Musk says the goal is around 1 million tons per year, yes, in about 3 years. That's the prerequisite for even dreaming of launching entire data centers up there. And it makes the launch dirt cheap. Where the internal cost level today is around $500 per kilogram to orbit, Starship is aiming for $10 to $20 per kilogram. So that's a reduction by a factor of 50 to 100. And that brings us to the second bottleneck, which is the technical heart of this video: the satellite itself. On June 18, 2026, just a few days before the IPO, Elon Musk presented the design of the first orbital data center satellite called AI-1 in an internal company meeting. And the numbers are remarkably specific. AI-1 delivers 150 kilowatts at peak and 120 kilowatts in continuous operation. The wingspan is about 70 meters. That's wider than a Boeing 747, whose wings measure just under 68.4 meters. When fully deployed, the satellite is about 20 meters tall. Most of this area is made up of the solar panels, which operate at a power density of 250 watts per square meter, resulting in an illuminated solar surface of about 600 square meters. Now to the famous cooling problem, the myth I mentioned at the beginning. Many people believe that you can't cool in a vacuum because there's no air or water to carry away the heat. That's not entirely true because it just works differently. Heat is released in space through radiation, specifically through large radiators that emit thermal energy as infrared light into the cold outer space. AI-1 is equipped with a deployable liquid radiator of about 110 square meters for this purpose. According to SpaceX, it radiates on both sides with redundant pump loops and integrated protection against tiny micrometeoroids. The trick is that an average data center on the ground can only get rid of its waste heat with difficulty and a lot of water, while here it radiates freely into the cold of space. That's exactly what Musk means when he says cooling is easier in space. SpaceX already has a benefit of the doubt here, because the company already operates over 10,500 Starlink satellites and has proven that it knows how to dissipate heat in orbit. And now comes the real punchline, which almost sounds paradoxical. According to Musk himself, this highly complex-looking AI satellite is actually easier to build than a regular Starlink satellite. The reason is surprisingly logical. A Starlink satellite needs highly complex antennas, huge phased array antennas and parabolic antennas communicating with millions of users on the ground. AI-1 doesn't need any of that. At its core, it consists only of a lot of solar cells, a large radiator, the actual computing module, and some laser links. That's it. According to Musk, there is no mysterious new technology here that still needs to be invented. A lot of it is simply solar technology. SpaceX has already developed this for the Starlink version 3 satellites, just bigger. So what does 150 kilowatts actually translate to in terms of computing power? Musk makes the comparison easy to grasp. A single AI-1 satellite is roughly equivalent to a single NVIDIA GB300 server rack, which, with its 72 graphics processors, draws around 140 kilowatts at peak on the ground. So you can imagine AI-1 as a rack of computing power in space. So a single satellite by itself isn't all that impressive. But, and this is the key, a single Starship can launch between 30 and 50 of these satellites at once. A single launch instantly delivers the computing power of 30 to 50 of these high-performance racks without buying land, without getting approval for the power grid, and without building a cooling infrastructure. The compute payload is interchangeable, so the module is not tied to a single chip manufacturer. SpaceX can use NVIDIA chips, upcoming generations like the Rubin series, or Google's Tensor chips depending on who is providing the best hardware at the moment. The data travels via laser links with a capacity on the order of 1 terabit per second, either from satellite to satellite or directly down to the existing Starlink fleet, which then relays it to Earth. And don't worry about the delay. AI-1 is flying at only about 600 kilometers altitude, and light travels roughly 300 kilometers per millisecond. This means the signal travel time is in the range of just a few milliseconds. Almost no noticeable delay. A quick aside about my own stuff, and I'll keep it brief. If this topic excites you as much as it does me, then please give the video a like. It's just one click for you, but it helps the channel a lot because YouTube will show the video to many more people. And if you want to support Mars Chronican even further, you'll find some nice extras in the channel memberships and in the shop, and you'll be directly funding this place. So that's it. And now back to perhaps the most exciting bottleneck of all. The chips, because this is where things really get big. The chips that go into AI-1 can initially just be bought on the market by SpaceX. The problem is the sheer quantity that the plan requires. According to Musk's estimate, the entire chip industry is heading toward a scale of maybe 100 gigawatts of AI computing power per year. That sounds like a lot, but it's nowhere near enough for the ultimate goal that Musk dreams of. Namely 1 terawatt, which is 1,000 gigawatts. To even be able to produce this next order of magnitude, a gigantic chip factory is needed, which Musk calls Terafab and already announced in March 2026 as a joint project of SpaceX, Tesla, and xAI, and the dimensions are absurd. The Terafab is supposed to have an area of around 100 million square feet. That's about 9.3 million square meters, or roughly 9 square kilometers. So about 10 times larger than the already huge Tesla Gigafactory in Texas. The estimated investments vary depending on the report, ranging from around $55 billion to over $100 billion. Elon Musk sums up the logic behind it in a straightforward way. Either they build the Terafab or they don't have enough chips. And they need the chips, so they build it. And now to the part you've wanted the most, the actual infrastructure on the ground. Because this is where the vision turns into concrete and steel. The center of all this is a new factory in Bastrop, Texas, east of Austin. It's called the SpaceX Gigaset. The site covers about 400 hectares or roughly 4 square kilometers. With a potential building area of around 1 million square meters, what makes it special is the complete vertical integration on a single campus. Not only will the AI-1 satellites themselves be built here, but the entire supply chain, from the solar ingots, meaning the raw blocks, to the wafers and finished solar cells, all the way to the circuit boards, will be built here. The electronic components, the user terminals, and the ground stations. In addition, there will be development and testing facilities, storage, and logistics. And this is not just a plan on paper. According to Musk, the facilities for solar production are already under construction, while the actual production building for the AI satellites is about to break ground. A semiconductor packaging facility at the same location already began installing equipment in April 2026. SpaceX wants to produce a reasonable quantity of these orbital data centers there by the end of 2027. At the same time, a solar factory with a capacity of around 10 gigawatts is being built in the region, just to supply the constellation with enough panels. How fast is all of this supposed to grow? I have to explicitly warn here, these are Musk's own goals, and he himself says that you should take them with a healthy dose of skepticism. They are not promises, but rather the best possible estimates. With this caveat, the plan is to reach an annual rate of around 1 gigawatt of AI computing power in space by the end of 2027. With 150 kilowatts per satellite, that alone means building over 6,000 AI-1 satellites per year. For comparison, the entire Starlink fleet today comprises around 10,500 satellites. From this 1 gigawatt, Musk wants to increase the capacity by an order of magnitude every year. So, to 10 gigawatts by around 2030, then to 100 gigawatts, and in the long term to that 1 terawatt. This one number, 1 terawatt, is roughly equivalent to twice the current total electricity consumption of the United States in space, just for artificial intelligence. Let's take a quick look elsewhere, because SpaceX is by no means alone with this idea, even if they have the biggest leverage. The American startup StarCloud was actually the first to send a powerful NVIDIA graphics processor into space at the end of 2025 and run an AI model there. And they are planning a constellation of 88,000 satellites with solar panels covering up to 4 square kilometers. Google is working on satellite data centers under the name Project Suncatcher, using their own Tensor chips, and plans to launch the first test satellites at the beginning of 2027. Jeff Bezos and Blue Origin have applied to the US Communications Authority (FCC) for a network of over 50,000 satellites under the name Project Sunrise. The chip giant NVIDIA has introduced dedicated space-ready AI platforms. And even Meta, Facebook's parent company, wants to collect sunlight from geostationary orbit at around 35,400 kilometers altitude to power data centers. And then there's China, which is taking a slightly different but already very concrete approach. Under the name Three-Body Problem Computing Constellation, a reference to the well-known science fiction novel, a Chinese consortium launched the first 12 of a planned 2,800 satellites in May 2025. These are not yet fully fledged data centers, but rather so-called edge computing, where the satellites process their data directly in orbit and only transmit the finished results to Earth instead of sending down huge amounts of raw data. The crucial difference from the American approach is that China's project is not driven by private companies, but is state-funded and established as a national strategy. For more detailed information about all these players, I refer you to our 2 deep dives on orbital data centers, which I have linked below. Finally, there's the most mind-boggling idea of all. And this is pure speculation and something for the distant future. Musk is already thinking beyond the terawatt. To grow by another factor of 1,000, Earth is no longer enough as a launch base. The only way SpaceX sees to achieve this is via the moon. The idea is to manufacture the solar panels and radiators up there directly from lunar material, so you don't have to haul all that mass laboriously up from Earth. And because the moon has no atmosphere and only 1/6 of Earth's gravity, you could launch the finished AI satellites into space from there without using a rocket at all. With a kind of electromagnetic cannon, a so-called mass driver. Basically a giant linear electric motor. That sounds like science fiction, and at the moment it is. But it shows the scale of thinking involved here. Let's get to an honest assessment, and once again, my opinion is clearly needed here. First, the mandatory disclosure. At the time of publication, I will personally hold a position in SpaceX stock, and I am explicitly not giving any buy or sell recommendation. This video is a journalistic analysis, not investment advice. Because it must be clearly stated, the timing of the AI-1 reveal just days before the biggest IPO in history was no coincidence. That was also a message to investors that SpaceX wants to extend its dominance in rockets and satellites into the lucrative AI business. And the business model is surprisingly down to earth. SpaceX simply wants to rent out computing power, just as it already happens on the ground today, where, among others, Anthropic and Google rent computing capacity from Musk's AI division for billions per month. But the biggest doubts about AI-1 are not about the physics, but about its economic viability. Launching servers into orbit, operating them there, and above all, never being able to maintain or upgrade them is simply more expensive than a warehouse in Texas. As long as electricity on the ground is comparatively cheap, it's completely unclear whether the whole thing will ever pay off. It's telling that Sam Altman, the head of OpenAI of all people, dismissed the idea of orbital data centers happening this decade as simply ridiculous. My assessment of this, the engineering behind it, is real, and much of it is actually just a bigger version of Starlink. That's true. But the leaps Musk is talking about, millions of tons into space, terawatts of computing power, a factory the size of a small town, are so enormous that you should take every single timeline with a grain of salt. It's quite possible that AI-1 will fly and work, and in the end still never be cheaper than a data center on the ground. And yet, and this is what I want to end with, this is exactly the kind of gamble that has always driven space exploration forward. A few years ago, anyone who talked about captured boosters and reusable rockets would have been laughed at. Maybe in 10 years we'll talk just as naturally about the first data center in orbit. Or it will remain an expensive, fascinating dead end. The only certainty is that serious work on it is already underway, with concrete in Texas and with steel in space. And that alone makes it a remarkable time to be alive. My name is Serwin, and this was Mars Chronican. Thank you for tuning in. Per aspera ad astra.